Imagine, if you will, a multi-million-dollar medical facility.
Right.
You have the absolute smartest scientists in the world working there.
Mm-hmm.
And they are backed by the most sophisticated equipment human engineering can possibly produce. I mean, the air is filtered, the lights are dimmed, the staff is incredibly highly trained.
Everything is dialed in.
Exactly. Everything is perfect. And yet, an entire operation, the fragile beginnings of dozens of human lives, is brought to an absolute standstill.
Just a complete halt.
Right, simply because a delivery driver walked down a hallway on the other side of a sealed door wearing a slightly too strong cologne, or, because someone bought a brand new plastic trash can for an office 3 rooms away. Welcome to the deep dive.
It really, it sounds like science fiction when you frame it that way.
It does.
But it is the absolute unvarnished reality of the world we operate in. You see, when you're dealing with single human cells, the scale of what constitutes a threat fundamentally shifts.
Yeah. And if you've been with us through our previous explorations of this topic, we spent a lot of time under the intense, dramatic glare of the microscope.
The microsurgeries.
Exactly. We've talked about microsurgery, about incredibly fine glass needles, and the precise, deliberate physical manipulation of cells.
Right, the active work.
But today, we are stepping away from the microscope stage. We're kind of lowering our voices today. We're going to explore something entirely invisible.
It really requires a completely different mindset. I mean, we are no longer looking at what we can actively do to a cell with our hands. We are looking at the empty space around it.
The mission of this deep dive is to explore what our sources call the invisible shield. We want to understand how an embryology lab functions as an artificial womb.
Yeah, that's the perfect term for it.
Because the lab is right. When I was poring over our sources for today, the image that kept forming in my mind wasn't a standard clinic with white walls and sterile counters.
What did it look like?
It felt extraterrestrial. I mean, a modern IVF lab is essentially a deep space capsule.
I think that is the perfect framework. It really is. Outside that capsule is a harsh, chaotic, completely incompatible environment that would instantly destroy the life inside.
Just immediately.
Instantly. But inside there is a perfectly engineered, self-contained biosphere. Every valve, every chemical scrubber, every heating element is working in absolute silent harmony to keep the crew alive.
What really struck me in the research was the overarching philosophy of that capsule.
Right.
The lab's job isn't to force biology to happen.
No, not at all.
You aren't in there with tiny microscopic paddles shocking the cells into dividing.
We can't force an embryo to grow. I mean, our entire job, the whole purpose of this deep space capsule is to eliminate environmental friction.
Environmental friction.
Exactly. We are trying to create an environment so utterly stable and so deeply secure that the biology can simply do what it naturally wants to do. We are basically getting the physical world out of the way.
Okay, let's unpack this. Because if we are going to understand this invisible shield, we need to understand exactly what we are shielding these cells from.
Right.
And to do that, it seems we have to start with the most visceral, fundamental requirement of life. Let's talk about the exact moment a cell leaves the human body and the immediate shock of the cold.
The thermal chain.
Yeah.
To truly appreciate this, you have to think about where these gametes, the eggs and the sperm, where they actually come from.
Inside the body.
Right. Think about the internal environment of the human ovary or the reproductive tract. It is a place of absolute complete darkness.
Pitch black.
Pitch black. It is perfectly moist. And above all, it possesses a constant, unwavering, deeply enveloping physiological warmth.
It's a sanctuary. It's an environment that has been refined by, millions of years of evolution to be perfectly still and perfectly warm.
Exactly. And the very millisecond those cells are retrieved by a physician,
The moment they come out.
the moment they exit the mother's body, they lose all of that evolutionary biological protection. They are entirely vulnerable.
Wow.
And the most immediate fatal threat they face in our world is the ambient temperature of a normal room.
Because a single cell doesn't have a circulatory system. I mean, it can't shiver.
No.
It has absolutely no way to generate its own heat to fight off the chill of the air.
None. Human gametes and early embryos have absolutely zero ability to self-regulate their internal temperature. So we operate at a strict, non-negotiable requirement of 37.0 degrees Celsius.
37.0.
Not 36.8, not 37.2, exactly 37.0 degrees.
See, that level of precision is staggering to me. Why is that specific decimal point so crucial? Like what physically happens inside the cell if the temperature drops to, say, 36.5 degrees?
To understand that, we have to look at the deep, delicate architectural machinery inside the cell, specifically when we're talking about the human egg. And the proper scientific term for the egg, which we really should use here, is the oocyte.
The oocyte. I always wondered about that spelling, with the double O at the start.
Yeah, it looks a bit strange written down. It comes from the Greek roots. Oion, meaning egg, and kaitos, meaning hollow vessel or cell. So oocyte.
Oocyte.
So as the oocyte matures inside the human body, it goes through highly complex, beautifully orchestrated stages of cellular division.
Mm-hmm.
We track this transition carefully in the lab, particularly from what is called the M1 stage to the M2 stage.
M1 to M2. So what exactly is happening during that specific transition that makes it so fragile?
During the transition from the M1 to the M2 stage, the oocyte forms a structure called the meiotic spindle.
The meiotic spindle.
Right. I want you to picture a microscopic, incredibly intricate web of cellular cables. We call these microtubules.
Okay, cable.
This web physically reaches out, grabs the UG's chromosomes, and holds them suspended in perfect, terrifying tension right in the center of the cell.
So it's essentially holding the actual genetic blueprint of a future human being.
Yes, exactly. It is waiting for the exact moment of fertilization so it can divide those chromosomes perfectly in half to combine with the sperm's DNA.
Wow.
But here is the terrifying part about the meiotic spindle. It is exquisitely sensitive to thermodynamics.
To heat.
To heat. If the temperature of that oocyte drops by even half a degree, the proteins that make up those microtubule cables lose their structural integrity.
Just from a half degree.
From half a degree, the delicate spindle will literally uncoil and dismantle. It physically falls apart inside the cell.
That is mind-boggling. I'm trying to visualize this tension. I'm picturing this meiotic spindle like the inner workings of a microscopic antique pocket watch.
That's a good analogy.
Right. You have this incredibly fine, tightly wound watch spring holding all the tension of the gears perfectly in place. The tension is necessary because pulling chromosomes apart requires actual physical force.
Yeah.
But if even a slight draft of cool air hits that microscopic metal, the cold makes it brittle, the spring violently snaps, and all the gears just fly out of alignment.
That is a phenomenal way to visualize it. And the consequence of that watch spring snapping is absolutely catastrophic for the cell.
Because it can't just be put back together.
But let's say the embryologist realizes the room is a bit cool and quickly warms the oocyte back up to 37.0 degrees.
Okay.
The spindle will try to reform, but it has to blindly rebuild that incredibly complex web of cables.
And if it makes a mistake?
If a single microscopic cable attaches to the wrong spot on a chromosome, when the cell finally divides, it will pull the genetic material unevenly.
Oh, no.
The cell will end up with the wrong number of chromosomes. This leads to devastating, unrecoverable genetic errors.
Just from that one mistake.
Yeah. The oocyte might still fertilize. It might even divide for a day or two in the lab, but it will eventually arrest. It cannot survive.
And all of that, a total irreversible failure of the genetic code, happens just because the plastic dish it was sitting in cooled down by a fraction of a degree for, what, a few seconds?
A matter of seconds, which is why the very first layer of our invisible shield is what we call the warm chain.
Warm chain.
To prevent that watch spring from ever snapping, every single surface an oocyte or an embryo touches must be actively, continuously heated to mimic the maternal body.
But how do you actually achieve that in practice? A laboratory is full of cold, hard materials. You've got stainless steel tables, glass microscope lenses, plastic test tubes.
It requires immense embedded infrastructure. When the physician is retrieving the fluid from the patient's ovary, the collection tubes don't just sit in a normal plastic rack.
What do they sit in?
They are instantly placed into solid, actively heated aluminum blocks. These blocks are bored out to fit the tubes perfectly, wrapping them in metal warmth from all sides.
So the transition from the body to the tube is like thermally seamless.
Precisely. And when the fluid is brought into the lab, the Petri dishes don't rest on cold microscope stages. They rest on highly specialized glass plates.
Wait, heated glass?
Heated glass. If you look closely at these glass stages, they are actually laced with transparent microscopic thermal wires that generate continuous heat.
That's incredible.
Even the air inside the enclosed isolates, the biological safety cabinets where we actually handle the dishes, that air is artificially heated and circulated.
So you are basically fighting the physics of the room. You're actively forcing the physical world to bend to the exact temperature of human blood.
Every single day, yes.
But here's where I get stuck. Heating a solid surface or putting a wire inside a piece of glass. I mean, that's just physics, right? That's thermodynamics. But the embryo isn't just sitting dry in a warm glass plate like a fried egg in a pan.
Oh, of course not.
It is submerged in fluid.
Yes, it is cultured in liquid.
Right. So doesn't the liquid introduce a completely different set of vulnerabilities? Like, the heat might be stable, but what about the fluid itself?
You've hit on the exact transition point between physics and chemistry.
Okay.
The thermal chain keeps the physical structure of the cell intact, but the fluid surrounding the cell controls its internal chemical reactions. This brings us to the second layer of the invisible shield. We call it the pH dance.
The pH dance. Okay, let's ground this for a second. pH is essentially the measure of how acidic or basic a liquid is, correct?
Yes, exactly. The pH scale runs from 0 to 14. 7 is perfectly neutral, like pure distilled water.
Right.
Anything lower than 7 is acidic, like lemon juice. Anything higher is basic or alkaline, like soapy water.
So where does a human embryo need to be on that scale?
For a human embryo to survive, its surrounding liquid must maintain a very specific, slightly alkaline physiological pH. We are talking about a tiny window locked right between 7.2 and 7.3.
That is a remarkably tiny window.
It has to be. Every enzyme, every protein inside the cell relies on tiny electrical charges to hold its specific three-dimensional shape. If the pH shifts, the electrical charges in the water shift. And if that happens, the cell's proteins literally begin to unfold and unravel.
They just fall apart.
They fall apart. So we place the embryos in a highly specialized liquid called culture media. But pure water alone doesn't naturally lock itself at a pH of 7.2 or 7.3. It fluctuates constantly based on whatever happens to be dissolved in it.
So how do you force the liquid to stay exactly in that 7.2 to 7.3 window? Do you just add chemicals?
We use a buffering system. Specifically, modern culture media utilizes a sodium bicarbonate buffer.
Wait, sodium bicarbonate? Like baking soda, the stuff sitting in the back of my refrigerator right now.
The exact same chemical compound.
No way.
It really is. But here's the trick. The bicarbonate dissolved in the liquid is only half of the equation. What's fascinating here, and what makes this a dance, is the dynamic relationship between the liquid media and the invisible air hovering directly above it.
The air. How does the air control the liquid?
Inside our incubators, where the dishes rest, we don't just use normal room air. We actively pump in a very specific, heavy concentration of carbon dioxide gas, CO2.
Okay, CO2.
That CO2 gas in the incubator atmosphere actively presses down on the surface of the liquid media and physically dissolves into it.
So the gas is constantly entering the liquid.
Yes. And when that dissolved CO2 gas meets the sodium bicarbonate inside the liquid, they engage in a continuous dynamic chemical tug-of-war.
The tug of war.
They push and pull against each other until they reach a perfect state of equilibrium. And that specific chemical tension locks the pH precisely at 7.2 or 7.3.
That is incredible. The liquid actually relies on the physical weight and presence of the gas in the air to maintain its own internal chemistry.
The air dictates the chemistry of the liquid, which is exactly why taking a dish out of the incubator and exposing it to normal room air is so incredibly dangerous.
Because normal room air doesn't have that heavy concentration of CO2.
Not even close. Normal room air has a tiny fraction of a percent of CO2. So imagine an embryologist takes a culture dish out of the incubator and sets it on the heated microscope stage.
Okay, the thermal chain is unbroken. The glass is warm.
Right, the temperature is fine. But the high concentration of CO2 that was dissolved in the liquid suddenly realizes that the room air above it is practically empty.
Ah, and nature hates a vacuum.
Exactly. Through simple diffusion, the CO2 gas rapidly rushes out of the liquid and escapes into the room air to try and balance the atmosphere.
It just off-gases. It evaporates right out of the liquid.
And the moment that CO2 escapes, there is nothing left in the liquid to pull against the bicarbonate. The chemical equilibrium shatters.
Wow.
Within minutes, the liquid media violently shifts and becomes highly basic, or alkaline. The pH spikes upward.
And as you mentioned earlier, when it becomes alkaline, the electrical charges change, and the proteins inside the embryo start to physically unravel.
The enzymes stop functioning, the cell's metabolism grinds to a halt, and all development stalls. It is a profound chemical shock.
Okay, stop. I have a very simple, probably naive question here.
Go ahead.
If the CO2 escaping into the room air is the entire problem,
Yeah.
why not just put a really tight, airtight plastic lid on the Petri dish.
Ah.
I mean, just seal the dish in the incubator so the gas gets trapped inside the liquid, and then when you take it out, the gas can't escape. Problem solved.
See, it is a totally logical thought. And honestly, in many other fields of biology, that is exactly what you would do.
Right.
But in embryology, it would be fatal. You have to remember what we were dealing with. An embryo is not a static piece of tissue. It is a rapidly dividing, living, breathing organism. It has a high-functioning metabolism.
Right, it's actually alive.
And because it is alive, as it grows, it is constantly consuming energy and producing its own microscopic metabolic waste gases.
Oh, I see where this is going.
If you put an airtight lid on that Petri dish, the cells literally suffocate. They require this dynamic open gas exchange to survive.
They need fresh air.
They need the fresh CO2 to come in to balance their pH, but they also desperately need their own toxic metabolic exhaust to be able to drift away into the atmosphere. An airtight lid would trap the embryo in a microscopic chamber of its own biological exhaust.
So you have this impossible paradoxical situation. You cannot seal the dish because the embryo needs to breathe and exchange gas with the environment. But if you leave the dish open to the room air for even a few minutes, the crucial CO2 escapes, the liquid becomes alkaline, and the cell goes into toxic shock.
That's the dilemma.
So how do you protect the liquid from the room air when the dish absolutely has to be handled under the microscope?
We can't use a solid plastic lid, so we use a different kind of barrier. We use a liquid barrier.
A liquid barrier. Okay, we are entering the absolute micro scale of the laboratory now.
We really are. To understand how this liquid barrier works, I need to paint a picture of just how small the world we are working in actually is.
Okay, paint the picture.
When we talk about culturing an embryo in liquid media, we do not use giant vats of liquid. We don't even use test tubes full of liquid. We culture them in microscopic droplets.
How microscopic are we talking?
Usually between 20 to 50 microliters in volume.
Let me try to contextualize that for the listener.
Right.
A single drop of rain falling from the sky is roughly 50 microliters.
Right.
So you are taking a developing human embryo and placing it inside a pool of water that is a fraction of the size of a single raindrop.
That is exactly the scale we operate on.
That sounds unbelievably fragile. I mean, if I drop a single raindrop on a warm kitchen counter, it's going to vanish into thin air in a matter of minutes.
And remember the first rule we established. Our countertops, our microscope stages, are actively heated to 37.0 degrees Celsius.
Right, the warm chain.
In a dry, climate-controlled hospital room, a 20 microliter droplet sitting on a 37-degree glass plate would evaporate incredibly fast. And evaporation is one of the most lethal, silent killers in the embryology lab.
Because if the droplet evaporates, the embryo is left sitting dry on the glass.
It actually dies long before the droplet completely vanishes.
Really?
Yes. The mechanics of how evaporation kills the embryo is the crucial part. When a droplet of culture media evaporates, only the pure water molecules turn into vapor and float away.
Right. Water evaporates, but the stuff dissolved in the water doesn't.
Exactly. The culture media isn't just pure water. It is a highly complex soup packed with salts, nutrients, amino acids, and proteins.
Okay.
When the pure water evaporates into the air, all of those salts and nutrients are left behind in a continually shrinking pool of liquid.
The concentration must skyrocket.
It does. We call this a spike in osmolality. The liquid surrounding the embryo becomes hyper-concentrated with salt.
And salt pulls water.
Exactly. Basic cellular biology dictates a fundamental rule of osmosis. Water will always move across a cell membrane to dilute a high concentration of salt.
Oh, wow. So the environment turns against the cell?
Violently. The high salt environment outside the embryo acts like a microscopic vacuum. It physically sucks the pure water out from inside the embryo's own cells to try and dilute the salty droplet.
It dehydrates the embryo from the inside out.
It shrinks, desiccates, and dies. The cellular membranes collapse. And all of this happens simply because a tiny fraction of water was allowed to evaporate into the dry room air.
So let's review the trap here. No tight plastic lids because they suffocate.
Right.
But if left alone, the warm raindrop evaporates and turns into a lethal, hyper-concentrated salt trap. What is the liquid barrier solution?
Mineral oil overlays.
Mineral oil, like actual literal oil.
Yes, highly purified, medical-grade, meticulously washed, and sterile mineral oil.
How does that work?
The embryologist takes the plastic petri dish, carefully places these tiny micro droplets of culture media along the bottom of the dish, and then literally floods the entire dish with a thick, heavy layer of this oil. The oil completely submerges and buries the droplets.
So the droplets are trapped at the bottom of a pool of oil.
Exactly. And because oil and water fundamentally do not mix, the oil acts as an impenetrable liquid shield over the droplets.
Uh,
The water molecules inside the droplet simply cannot cross the heavy oil barrier to evaporate into the air above.
it locks the moisture in. It physically pins the water down.
It locks the moisture perfectly, which means the osmolality, that incredibly delicate salt concentration, is locked permanently in place. The embryo will never dehydrate.
That's brilliant.
It is. But the true brilliance of the mineral oil overlay is that it serves as a multi-tool. It does so much more than just stop evaporation. Think back to the pH bands and the thermal chain.
You mean the escaping CO2 gas and the dropping temperature? Does the oil stop those too?
It acts as a profound physical buffer for both of those elements. Remember, we said gas needs to exchange.
Right, the exhaust.
Gas can slowly diffuse through mineral oil, which allows the embryo to breathe and release its exhaust. But the thick layer of oil drastically slows down the rate at which the CO2 escapes when the dish is temporarily taken out of the incubator. It turns a rapid spike into a very slow, manageable drift.
It buys you time under the microscope.
It buys us precious vital minutes to perform our work without shocking the cells. And thermally, it acts as a liquid blanket.
Because oil holds heat.
Exactly. Oil retains heat differently than water or air. It insulates the droplets, meaning they cool down much, much slower than they would if they were exposed directly to the draft of the room. The oil is arguably the most important mechanical tool in the artificial womb.
It's amazing when you stack it all up. We have the thermal chain providing the exact warmth of the human body.
Yes.
We have the CO2 gas actively dissolving into the liquid to balance the internal pH chemistry. We have a thick blanket of mineral oil protecting the physical droplet from salt spikes and temperature drafts. So at this point, the cell is warm, chemically balanced, and perfectly hydrated. Can we finally just let them breathe the clean air of the laboratory?
You would think so.
Right.
But this is where we encounter one of the most fascinating and counterintuitive contradictions in our biology. We call it the oxygen paradox.
The paradox, meaning the air we breathe is somehow a problem.
Ambient room air, the exact air that you and I are breathing into our lungs right now, is roughly 21% oxygen. For an adult human, that is life-sustaining. Our bodies are designed to process it.
Sure, oxygen is the fundamental fuel of mammalian life. We need it to survive.
But if we look inside the human body, specifically deep inside the fallopian tubes in the uterus, where a natural embryo develops for the first 5 to 6 days of its life, the environment is completely different.
Different how?
The oxygen concentration deep inside the female reproductive tract is incredibly low. It ranges from only 2% to 7%.
Wait, really? That is a massive difference. 21% out here in the world versus maybe 5% inside the womb.
It is a drastic difference. And for decades, in the early days of IVF, embryologists didn't fully appreciate this.
They just use normal air.
Yes, embryos were cultured in standard incubators that just utilized normal 21% room air. But over time, scientists realized that high oxygen is actually deeply toxic to early embryonic cells.
Wait, I have to push back on this because it goes against literally everything I learned in 6th grade biology.
That sounds wrong.
Human beings literally require oxygen to survive. It is the fuel for our cellular engines. If you drop the oxygen down to 5%, shouldn't the cell suffocate? How does oxygen act as a poison?
To understand the paradox, you have to look at how the cellular engine actually works. You are right, the mitochondria inside the cell use oxygen as fuel to generate energy.
Oh.
But it is an incredibly messy, volatile process. When an embryo processes oxygen, the metabolic reaction naturally produces dangerous chemical byproducts.
Like exhaust.
Yes, metabolic exhaust. In a high 21% oxygen environment, the tiny embryonic cell is flooded with far too much fuel. Its metabolic engine goes into overdrive and it burns too hot.
It's like flooding an engine.
Exactly. This creates a massive excess of highly unstable molecules called reactive oxygen species, or ROS.
Reactive oxygen species. I think I've heard them called free radicals in, nutrition articles.
Free radicals is a common term, yes. These ROS molecules are chaotic and deeply destructive. They are actually missing an electron, so they violently tear through the inside of the cell, aggressively stealing electrons from anything they touch to try and stabilize themselves.
They're like microscopic vandals, just ripping the cell apart looking for spare parts.
That is exactly what they are. They attack the cell's lipid membranes, they damage the mitochondria themselves, and most devastatingly, they physically attack and fracture the cellular DNA.
The DNA itself.
Yes. This state of constant cellular damage is called severe oxidative stress.
Oxidative stress. It's almost like the high oxygen in the room air is literally rusting the embryo from the inside out.
Biological rusting is a perfect analogy. Left in 21% oxygen, the embryo rusts. So modern embryology had to find a way to stop this rusting and recreate the dark, low-oxygen sanctuary of the fallopian tube.
How do you do that?
The solution is what we call tri-gas culturing.
Tri-gas, meaning 3 distinct gases inside the incubator.
Yes. We already know we use ambient air, and we add heavy carbon dioxide CO2 to press into the liquid and manage the pH.
Right.
But to solve the oxygen paradox, modern incubators pump in a massive continuous amount of a third gas, pure nitrogen or N2.
Nitrogen. How does adding a gas lower the oxygen?
Nitrogen is an inert gas, meaning it doesn't react with the cells, but it takes up physical space. The incubator uses the heavy nitrogen gas to actively displace and push the oxygen out of the enclosed chamber.
Oh, it crowds it out.
Exactly. We flood the incubator with nitrogen until the oxygen level is forced all the way down from 21% to a safe physiological 5%.
You're literally choking out the atmosphere of the room to save the cell.
If we connect this to the bigger picture, lowering the oxygen is just another way we act as an invisible biological shield. We're using heavy industrial gases to artificially recreate the deep internal low oxygen protection of the maternal body. We are silencing the oxidative stress so the DNA remains perfectly intact and the engine doesn't burn itself out.
Okay, so normal room air has too much oxygen and it rusts the cells. We fix that by pumping in nitrogen.
Right.
But outside the incubator, in the broader lab, surely the air in the room itself is just clean air. Right? I mean, it's a medical facility. The floors are mopped. The staff wears scrubs.
The concept of what constitutes clean air takes on a terrifyingly specific definition when you are dealing with single cells that have no defense mechanisms.
Terrifyingly specific. What are we missing?
Because the most dangerous things floating in the air of a normal building are not dust particles or even bacteria. The most dangerous things are completely invisible. They're highly mobile, and to us, they often smell quite pleasant.
Smell pleasant.
We need to talk about volatile organic compounds, VOCs. These are carbon-based chemical vapors that continuously off-gas from solid and liquid materials into the air.
Okay.
If you think about your daily life, you and I breathe them in every single day, by the millions, without any consequence whatsoever. Our adult bodies easily process and ignore them.
What kind of everyday things release VOCs?
Think about your morning routine today. The scented shampoo you used, the deodorant you put on, the leather seats in your car.
Wow. Okay.
When you get to the office, it's the whiteboard markers, the floor cleaners used by the janitorial staff, the hand sanitizer sitting on your desk. The list is shockingly mundane.
Really?
Perfumes, colognes, hairsprays, even the invisible off-gassing from something as simple as a brand new plastic trash can or a fresh coat of paint on a wall.
Here's where it gets really interesting. Earlier, I used the example of a new plastic trash can bringing down a facility. You were telling me a piece of standard office equipment could actually ruin an IVF cycle.
It absolutely can. And historically, in the early days of the field, before we understood the sheer toxicity of these vapors, things exactly like that did happen.
You're kidding.
No, unexplained drops in embryo survival were eventually traced back to new linoleum flooring or fresh paint in an adjacent hallway.
But how? How does the smell of a trash can or the vapor from someone's lavender hand soap actually hurt a microscopic embryo resting under a layer of oil?
You have to remember the biological reality of the embryo at this stage. It is a cluster of perhaps a few dozen cells.
Right.
It has no liver to detoxify its blood. It has no lungs to filter the air. It has no immune system or white blood cells to fight off chemical invaders. It is completely naked to the environment.
So when a VOC vapor is floating through the lab,
if a vapor from a scented soap or a harsh floor cleaner floats through the lab air and settles on the surface of a culture dish, those carbon molecules are highly lipophilic.
meaning they love fat and oil.
Exactly. They can actually dissolve straight through the mineral oil overlay we rely on. They pass right through the oil and into the water of the culture media.
They breach the liquid shield. The oil stops the water from getting out, but it doesn't stop the chemical vapor from getting in.
Precisely. And once those toxic VOC molecules dissolve into the liquid, they enter the embryo's cells. The chemicals bind to the internal proteins and damage the cellular machinery.
Oh, wow.
Because the embryo cannot process or excrete the toxins, the cell realizes it is fundamentally poisoned and irreparably damaged. And so it triggers a catastrophic biological failsafe. We call it cellular apoptosis.
Apoptosis, that's programmed cell death, right?
Programmed cell death. The embryo initiates a self-destruct sequence to prevent a mutated, chemically damaged organism from forming.
It just gives up.
Entire cohorts of beautiful, rapidly developing embryos will suddenly just arrest and die overnight because of a microscopic spike in VOC vapors.
That is chilling. A blastocyst, a potential human life, completely shutting itself down and dying because a delivery driver wore too much cologne or someone washed their hands with a floral soap down the hall.
Which is exactly why there is a draconian, absolute zero-tolerance policy for any fragrances or harsh chemicals in an IVF clinic.
I imagine so.
It is not a preference. It is a clinical mandate. Staff cannot wear perfume, cologne, or scented lotions. They use specialized, unscented, VOC-free soap.
Wow.
We use highly specific, heavily regulated cleaning agents for the floors and counters. If a delivery person walks into the clinic wearing heavy cologne, they're often physically not allowed past the front desk, let alone anywhere near the sealed lab doors.
I completely understand the ban on perfumes, but you can't control everything in the modern world. I mean, a patient might walk into the retrieval room wearing hairspray.
True.
The building materials themselves, the drywall, the ceiling tiles, might naturally off-gas over time. If you can't even have scented soap in the building, how does a lab actually scrub the air of the chemicals we can't even smell or see?
That brings us to the actual architecture of the cleanroom itself, the physical anatomy of the laboratory space.
Because an IVF lab isn't just a room with scientific equipment sitting on tables.
No, the room itself is the most important piece of equipment. It is an industrial-scale air handling engine. To protect against these invisible chemical threats, the air inside a certified IVF cleanroom is completely pulled out, replaced, and scrubbed through massive filtration banks multiple times every single hour.
So the air is constantly moving, constantly being refreshed.
Constantly. And to understand how we strip the toxins out of it, I want to take you on a sort of a lab spotlight tour.
Okay, let's do it.
I want you to imagine we set up a tall ladder right in the middle of the lab, and we climb up and push open one of the heavy sealed acoustic ceiling panels above our heads.
Okay, I'm climbing the ladder. I'm poking my head up into the ceiling plenum. What am I looking at in the dark up there?
You are looking at a massive, complex network of heavy ductwork and multi-stage filtration units that hum like jet engines.
Mm-hmm.
The air from the outside world is pulled into the building and forced through a brutal two-part filtration system before it ever touches the lab floor where the embryos are.
What's part one?
Part one is the physical filtration, the HEPA filters.
High-efficiency particulate air.
Correct. These are dense, heavily pleated filters that act as an incredibly fine physical net. They trap 99.97% of physical particulates floating in the air.
So dust and stuff.
Right. Microscopic dust, microscopic flakes of human skin cells, clothing fibers, and highly dangerous fungal spores or ambient bacteria that ride on those dust particles like little rafts. The HEPA filters catch all the solid matter.
But wait, a HEPA filter is just a woven net. It catches solids. A VOC molecule, the smell of cologne, is a gas. It's a chemical vapor.
Yes.
It would just pass right through the physical net of a HEPA filter like wind through a chain link fence.
Exactly. Which is why part two of the ceiling architecture is arguably the most critical element for an IVF lab. The chemical sponge.
The chemical sponge. Sounds intense.
It is. In the heavy ductwork, directly after the HEPA filters, the air is violently forced through massive, heavily compressed beds of specialized pellets. We are talking hundreds of pounds of these pellets.
What are they made of?
They are made of two specific materials, activated carbon and potassium permanganate.
Activated carbon. Like what's inside a high-end water filter pitcher in my fridge, but on an industrial scale?
Yes, but the scale of the surface area is difficult to comprehend. Activated carbon is incredibly porous. On a microscopic level, a single pellet is filled with millions of jagged little caves, tunnels, and crevices.
Okay.
A handful of this carbon has the internal surface area of an entire football field. As the VOC gas molecules pass through this bed, they get physically stuck. They wedge themselves inside these microscopic carbon caves.
So they are physically trapped in the dark.
Trapped. But trapping them isn't enough because eventually the carbon would fill up and start releasing them back into the air.
Oh.
That is where the potassium permanganate comes in. It is a powerful, aggressive oxidizing agent. Once the toxic VOC molecule is wedged inside the carbon, the potassium permanganate chemically attacks it.
It attacks it.
It strips electrons away, breaking the carbon bonds of the VOC and physically tearing the invisible vapor molecule apart.
So it's not just trapping the poison, it's chemically neutralizing it. It is fundamentally altering the shape of the molecule so it no longer acts like a poison.
It is destroying its chemical signature entirely. By the time that air pushes out of those chemical beds, down through the ceiling vents and into the laboratory where the embryologists are working, it is virtually entirely free of dust, bacteria, fungal spores, and volatile organic compounds.
That is amazing.
It is genuinely some of the purest, most pristine air on planet Earth.
But there are doors to the lab. I mean, people have to walk in and out. The doctors have to bring the fluid in from the operating room.
Yes, they do.
How do you keep all that perfectly scrubbed, pristine air inside the lab and the dirty, cologne-scented hallway air outside?
Through the invisible physics of positive air pressure.
Positive pressure, how does that work?
Those massive jet engine fans we saw up in the ceiling are deliberately calibrated to pump this clean, scrubbed air down into the lab space slightly faster and more forcefully than the air can naturally escape under the doors or through the vents.
So you're overinflating the room.
Exactly. You are pumping more air in than can get out. The atmospheric pressure inside the clean room becomes physically higher than the ambient pressure in the adjacent hallways, the locker rooms, or the operating theaters.
It's like a balloon.
Yeah.
When you blow up a rubber balloon, the pressure inside is immense, straining against the walls.
Right.
And if you suddenly open the neck of the balloon, the outside air doesn't go in. The high-pressure air violently rushes out.
That is the perfect analogy. When an embryologist opens the heavy, sealed clean room doors to walk into the lab, the dirty hallway air cannot enter.
Because the wind is pushing it back.
Exactly. The high pressure inside forces a physical, invisible wall of clean air to violently rush out through the doorway, blowing outward into the hallway. It physically pushes away any dust, any vapors, or any microbes trying to drift in. It creates a continuous physical wind barrier that protects the inner sanctum.
That is just staggering. The sheer scale and interconnectivity of the engineering.
It's a lot.
Let's just review what we've built here. We have heavy aluminum heating blocks and microscopic glass wires, maintaining a relentless 37.0-degree warm chain so the watch spring doesn't snap.
Right.
We have heavy CO2 gas actively dissolving into the media to balance the bicarbonate pH so the enzymes don't unravel. We have layers of sterile mineral oil locking in the water so the salt doesn't spike. We have pure nitrogen gas suffocating the room's oxygen to prevent oxidative rusting of the DNA. And above it all, we have jet engine fans pushing air through carbon caves to chemically assassinate toxic perfumes while overinflating the room to blow away the outside world.
It is a symphony of physics, thermodynamics, and chemistry, all running simultaneously.
But here is the thing that makes me deeply anxious just talking about it. That is a massive, highly complex, interconnected machine.
Yes, it is.
And machines, by the laws of entropy, break. The power grid goes down. A gas cylinder runs empty. A heating wire short circuits. How on earth do you know if one tiny piece of this invisible shield fails in the middle of the night on a Sunday when the lights are off and everyone has gone home?
You've just described the absolute nightmare scenario for every embryologist on Earth.
I would never sleep.
And it is exactly why we rely heavily on the continuous sentinel.
The continuous sentinel, what is that?
Human beings have to sleep. We cannot physically stand watch in the lab 24 hours a day, but the digital networks can. High-standard, modern laboratories are wired with an extensive, highly sensitive telemetry sensor grid.
Telemetry, so remote continuous monitoring.
Yes. And importantly, these are independent third-party electronic sensors.
Meaning they aren't part of the equipment itself?
Right. An incubator has its own internal computer to regulate its temperature and gas, but we absolutely do not trust it to govern itself. We place completely separate, independent digital probes inside every single incubator chamber, inside every single refrigerator where we store the media, and inside every single liquid nitrogen storage tank where frozen embryos rest.
So it's essentially a third-party alarm system constantly watching the machines that watch the embryos.
Exactly. And the sensitivity of these sensors is microscopic. If the CO2 gas line feeding an incubator drifts by a mere 0.3% from its target,
or if a wire breaks,
or if the thermal element in a heated glass shelf experiences a microfluctuation of 0.5 degree, the telemetry system immediately recognizes the breach.
then what does it actually do? Does it just flash a red warning light in a dark, empty lab?
Oh no, it acts instantly and aggressively. The system triggers a cascading alarm protocol. It immediately sends automated text messages, emails, and actual synthesized voice phone calls to the smartphones of the on-call embryologists, the lab director, and the facility managers.
So it's physically waking people up at 3 in the morning.
Without hesitation. The moment that phone rings, the embryologist will log into the telemetry system remotely from their home. assess the drift, and if necessary, drive straight to the clinic in the middle of the night to physically switch out a malfunctioning incubator or change a gas tank.
Wow.
And they do this before the internal temperature or the pH ever has the chance to reach a critical danger zone for the embryos.
It catches the failure before the failure has time to hurt the cell.
Exactly.
Yeah.
The continuous sentinel ensures that an equipment malfunction never has the opportunity to escalate into a clinical emergency.
So that's the night shift.
Mhm.
The machine's watching the machines. But what happens when the sun comes up? The embryologists arrive, they take off their street clothes, they walk through that positive pressure wind barrier and step into the clean room.
Right.
What is the very first thing they do?
They do not touch a single patient cell.
Really? With all that technology, you don't just get right to work.
Absolutely not. The first hours of every single working day in an IVF lab are entirely consumed by rigorous, uncompromising, daily quality control rituals.
Quality control.
Before the first oocyte retrieval of the morning, before the first frozen embryo thaw, the morning team must physically, manually validate the invisible shield.
What does that validation actually look like?
It is an exercise in absolute relentless repetition. The embryologists take external, highly calibrated, certified digital thermometers and physically measure the temperature of every single heated stage, every aluminum block, and every incubator shelf to ensure they are holding exactly 37.0 degrees.
Verifying the warm chain by hand.
Then they take heavy handheld gas analyzers machines that sample the actual air and plug them directly into the external sampling ports of the incubators.
Okay.
They manually draw out the gas to verify that the CO2 is perfectly balanced for the pH dance and that the nitrogen has successfully driven the oxygen down to that 5% threshold.
Verifying the tri-gas environment.
They check the pressure gauges on the massive liquid nitrogen tanks. They run handheld air particulate counters in the center of the room to confirm that the HEPA and carbon filters up in the ceiling are still scrubbing the air efficiently.
That is a lot of checking.
They record every single decimal point, every single measurement in a massive continuous quality control log.
It sounds utterly exhausting before the workday even begins.
It is the foundation of science. Consistent clinical success is built entirely on this foundation of absolute daily repetition. We must physically verify the performance of our tools and our environment before we ever dare to rely on them to protect human life.
You know, hearing all of this, it raises a really interesting point about the way patients perceive this whole process.
How do you mean?
Because when a patient goes through IVF and they get that devastating phone call on day 3 or day 5 that their embryos stopped growing.
This raises a very important question, yes. The gap between the myth and the clinical reality.
Right. The immediate visceral thought for a lot of people is the lab did something wrong. The lab dropped the dish, or the lab let bacteria in, or the lab's incubator broke in the night and killed my embryos.
Yeah.
It feels like a failure of the facility.
And that is an entirely understandable, deeply human reaction to grief and profound disappointment. It is natural to look for an external cause when something goes wrong.
Of course.
But when you understand the sheer magnitude of the invisible shield we've just spent an hour discussing, the thermal chain, the bicarbonate buffering, the mineral oil overlays, the positive air pressure, the carbon scrubbers, the continuous telemetry, the daily manual calibrations.
It makes ambient bacterial contamination or an operational temperature crash seem practically impossible.
It is incredibly, incredibly rare in a modern certified laboratory. The reality is much more complex and often much harder for a patient to hear.
Why is that?
Because we have this bulletproof invisible shield, we know definitively that the external environment is perfectly stable. Therefore, when a cohort of embryos experiences a sudden developmental drop or a total arrest, it is almost always due to inherent, profound chromosomal or cellular limitations locked deep within the gametes themselves.
The antique watch spring was already compromised before it even left the body.
Precisely. The genetics of the egg or the sperm simply did not possess the correct biological instruction manual required to continue dividing. It is a fundamental biological limitation, not an operational cleanliness failure.
I see.
The lab's environment was perfect. The biology simply could not overcome its own internal hurdles.
So what does this all mean if we step back and look at the entire deep space capsule we've just explored? I think it means that an IVF clinic can hire the greatest, most talented microsurgeons on Earth.
They absolutely can.
They can have the steadiest hands, the sharpest glass needles, the absolute best surgical technique. But without the invisible, unyielding consistency of filtered air actively heated surfaces, and meticulously balanced gas mixtures. All of that manual skill means absolutely nothing.
Nothing at all.
The outcomes will fail.
The environment is the ultimate foundation. Without it, the science collapses.
It really is. It completely changes the way you look at a medical clinic.
Yeah.
Precision environmental care, this obsessive paranoid control over invisible variables, isn't just a regulatory requirement to pass an inspection.
No.
It is arguably the highest, most profound physical expression of a laboratory's devotion to its patients.
If I can leave you with one final thought to ponder as we step out of the clean room today,
Please do.
consider the incredible, almost absurd paradox of human engineering that we've just discussed. We spend tens of millions of dollars building these facilities. We construct massive air-handling engines filled with chemical carbon beds. We pump in heavy industrial nitrogen and carbon dioxide gases. We design microscopic thermal wires into glass. We deploy 247 laser telemetry grids and synthesized alarm systems, all to perfectly recreate a microscopic environment that the human female body effortlessly maintains, completely in the dark, without a single conscious thought every single day.
Wow. That is profoundly humbling. It really highlights the sheer, staggering complexity and perfection of natural human biology.
It truly does. It's a miracle we can even come close to replicating it.
Well, if today was about the invisible environment, our next deep dive is going to step directly into the digital frontier.
Oh, this will be a good one.
I want to gently tease episode 21, which will be our exploration into artificial intelligence and time-lapse technologies. Because now that we know how perfectly stable and painstakingly balanced this incubator sanctuary is, the absolute last thing we want to do is open the door, pull the embryo out into the cold room air, and disrupt the shield just to look at it under a microscope.
Exactly. The less we disturb them, the better they grow.
Next time, we will explore how continuous internal video monitoring and incredibly advanced AI morphokinetic algorithms are allowing embryologists to evaluate cell division and development minute by minute, scoring and ranking embryos without ever taking them out of the warm chain, without ever exposing them to the room air or the VOCs.
It is the next true evolution of the invisible shield.
I can't wait to unpack that.
Yeah.
But until then, the next time you walk into a building, smell a new coat of paint, spray a countertop with cleaner, or feel a draft of cold air, take a moment to appreciate the incredible resilience of your own adult biology. Because in the micro world of the deep space capsule, those invisible forces are the difference between life and death. Keep questioning the invisible forces around you. We'll see you next time.